Hello everyone, we are Team Dark Knight. We present you the demo of our project on information theory based network consolidation. First, let me tell you why we chose this project. The power consumption in today's network is increasing at alarming rate. So this is a big concern in today's network. So there is a need to limit the power consumption in the network. So a simple idea that we used for controlling the power is by controlling the packet flow. As you can see, the packet flow is directly proportional to the power consumed. Let me show you with an example. So the power is measured for each packet. So when it is found to be greater than the threshold, then we control the packet flow, we reduce the packet flow in order to bring down the threshold.
Now let us look at few network applications and compare their performance in software and hardware implementation. Here we see an encryption application with a static key known to both to the server and the client. We have the server on the right and the client on the left. Now we see that the encrypted packets are being sent and decrypted on the server. The timestamps have been recorded and we see an average transmission time of 525 milliseconds. Now let's check the same application in hardware where the encryption module is built as an hardware accelerator on network processor. So the right hand side is again the server and the left hand side is the client. We are starting up the server right now and we'd be sending packets. As you can see that the encoded packets are sent and the decoded packets are displayed on the server. As you can see, the sequence of the number is same, so that means that the packet has been decoded properly, and the is difference in transmission is 44 milliseconds. Here the static key was known both to the client and the server. Now let's see what happens if I change the static key. I'm making the static key as 100. Now the client has a different static key and then the server has a different static key. Now let's run the same thing again and see what's the difference. As you can see that the numbers are not in sequence and there is some other characters in between. So that means it has not been decoded correctly.
Now, let us see the software implementation of another network application. Here we have encoding. On the right hand side, we have server. On the left hand side, we have the client. So the client side, the packets are encoded, and on the server side, it's decoded. And we see the average transition time is 299 milliseconds. Now let us see the hardware implementation of the encoding technique. On the right hand side, we have the server. On the left hand side, we have the client. The packets are encoded on the client side, and you can see the encoded packets are decoded on the server side. On the server side, you can see the packets are in a sequence. That means that the encoded packets are decoded back. Also, the average transmission time is far less than the software, that is 35 milliseconds.
Now let's look into the power management system. We have two nodes which are active here, N0 and N3. I'll be setting one of them as server. The threshold for power, which in our system is the maximum number of transitions, is set using a Perl script. In this first trial, I'll be setting it to a very high value of 10,000. We now access two software registers, which holds the total number of transitions in the packet and the corrected value, which is used to regulate the flow of the packet. As you can see, the accumulated power, which is nothing but the corrected value, is about 375, and the total number of transitions is 389. With the threshold kept same, let us now send a bigger packet. I would be doing this using iperf. Let's just send a set of these. Bigger packet would mean a lot more transitions, and this can be observed in the software register values. As you can see, the sum has increased, but as this is way below the threshold, there is no correction made on the accumulator value. Let us now reduce the power threshold to a very low value of 200 and send a similar packet. The threshold is set to 200. Now let me just open a server and send a packet. Let us now measure the total number of transitions and the accumulated value. As you can see, the total number of transition is somewhat close to what it was the last time, but the accumulated value is now 200, which is nothing but the threshold. So we see that the accumulated value has been corrected in a way decremented, thereby introducing a delay and regulating the packet flow.